Okay, we are back. We've proved limit law 1. Hopefully that made sense. Let's go. We're going to now prove limit law 2. That the limit of the sum is the sum of the limits. How are we going to do this? Well, first of all, once again, this is built into this is the assumption that these limits on the right both exist in our numbers. So the limit as x, so say that the limit as x approaches c of f is some number like L, and so I'll just write like let the limit as x approaches c of f be L, and let the limit as x approaches c of g be m. Okay. And yeah, what do I therefore need to show? I need to show that the limit as x approaches c of the f plus g function is L plus m. Okay, so what is the f plus g function? It's just a function whose outputs for any input is just the sum of the outputs of f and g. Alright, so that's still just kind of talking without really doing anything. Let's see, what should I do? Well, I guess I should just draw some pictures now. So let's see, here is a kind of a picture. Here's kind of like another picture, and maybe here's a third picture, but I messed that up. Okay, so picture. Picture, and right, we have these functions. So what's up? So we have some function f. You know, it's doing like this. Here we are at c, and the answer is that this is going to be pretty much L. And I have some function g, which looks like who knows what it looks like. It doesn't really matter. And this is pretty much m, and now there's like the f plus g function. What is the f plus g function? It's the function which is going to be, you know, bigger, right? So if you're trying to do this accurately, okay, I'm not trying, but if you're trying, it's going to be bigger, right? It's going to be the sum of these two. So by the time I get to c now, it's going to be way up here at like L plus m. That's not totally accurate, but in fact, kind of annoying for what I'm trying to do, but I think this is the idea. Okay, putting these pictures aside kind of for a second, we're going to come back to them. I think once you talk this out, it's just really easy. So let's just go. So what do I know? Well, I know that the limit as x approaches c of f is L. So therefore, what I know is that, well, this limit is L. So I have the full epsilon-delta definition for this particular limit. In other words, what I know is for any epsilon greater than 0, there exists a delta greater than 0 such that for all x, and here I think it's nice to not use the absolute value version, but to use kind of the more casual version, which is to say that in between c minus delta and c plus delta, all of those x values, when plugged into f, land between L minus epsilon and L plus epsilon. Chop, chop, chop. Okay, and maybe you want to be more careful and say, like, you know, let's not talk about c itself, because this is supposed to apply even if these functions are undefined at c, the limit is unaffected. Okay, so this here I am just this is just because, right? So the limit as x approaches c of f of x is L. So this is the definition. So I sort of know this already. And also, I know that the limit as x approaches c of g of x is m. So what is it that I know? I know that for all epsilon greater than 0, there exists a delta greater than 0 such that for all x, if I am pretty close to C, specifically if I'm within delta, then my G function will be between m plus epsilon and m minus epsilon. Okay, good. And then, what is it that I want to prove? Well, what I want to prove is that maybe I want to rewrite it sort of right here. What I want to prove is that the limit as x approaches c of f plus g is L plus m. That's what I need to prove. And then I can just kind of erase this because it's sort of in the way. Yeah. Okay. And well, all right. What does that mean? What I need to show is that for all epsilon greater than 0, there exists a delta greater than 0 such that for all x, and now I need to figure out, okay, how far away from x can I stray this time so that, well, what? So that the f plus g function, so I'll write it here as f plus g, is between, is not too far away from the limit. What's the limit? Supposedly L plus m. So this here I'm going to write L plus m minus epsilon, and here I'm going to write L plus m plus epsilon. Okay, so here I'm just like writing a lot of things and not even really doing anything at all yet. But this is what I need to prove. So just kind of talking it out, you know, for maximum clarity, what's happening? I'm focusing now on the thing I'm trying to prove. And here's the L plus m function. What's going to happen? I'm going to get challenged with an epsilon. This time I'm drawing pictures because I think it's better this way. Here's my f plus g function. Here's the y value, L plus m. What is the logical structure of the thing that I'm trying to prove? Well, I get challenged with an epsilon. What is epsilon? It is how far, it's how close my function needs to be to L plus m. So that's L plus m plus epsilon, and that's L plus m minus epsilon. And okay, great. What do I have to do to meet that challenge? To meet that challenge, I have to figure out how close to C I must be in order for that to be true. So that's C plus delta, C minus delta. So in other words, I get challenged with an epsilon, and I respond with a delta, and that delta tells me how far away from C I can stray, and if all the x values that are at most delta away, or that are less than delta away, when I plug them into the function, if they land between the blue parallel lines, then I win, and I've proven the thing that I'm trying to prove. Okay, so the whole strategy for this proof is to just kind of get, you know, receive this challenge is epsilon, and then to find a response. Okay, but of course, what is the f plus g function? It's just the f function plus the g function. And what do I know about these f and g functions? Well, I know a lot about their behavior near C. Specifically, I know that the limit of f is L and the limit of g is m. So I sort of already know that no matter how close you would like me to be to L, I can get that close by just getting sufficiently close to C. Okay, in other words, no matter what challenge you give me, I can get really, really close to C and meet that challenge. And I also know that the limit as x approaches C of g is m. So I know for this g function that no matter how close you want me to be to m, I can get close enough to C so that that's true. And so now what? Well, you have to maybe feel a little bit that what is the f plus g function? I've said this already 3 times. It's just the f function plus the g function. So all the y values are going to get added. So what is f plus g? At every single sort of point, the f plus g function is just the sum of the y values of the f and g function associated with that point. So, what does that say about the errors? If I'm only allowed to be off by epsilon in the f plus g function, then one way to achieve this maximum error of plus or minus epsilon would be if my f and g functions were off by only, say, half an epsilon from L and M, respectively. Okay, and so now I'm going to just sort of draw that in here. In other words, imagine that I was only off by epsilon over 2 and in the positive and negative direction from L. And imagine that I was only off by epsilon over 2 in the away from M in the g function. Well, if that were true, then when I added these two together, I would be off by at most epsilon. In other words, all I need to do is focus my attention on some x values for which this is true and this is true, and then automatically when I add the two functions together, this will be true. Alright, so this is the whole proof right here, right? The thing is that because this limit as x approaches c of f is L, then there is a small interval for any possible challenge. And so now what I do is I go right here and I say, okay, challenge. My challenge is epsilon over 2. Yeah. Do I have enough room for this? Let's see. Maybe I'll write it over here. My challenge is, challenge epsilon over 2. And then there's a response. What is the response? The response is how close to C I must be in order for my outputs to be within epsilon over 2 from L. Let's call that response delta 1. Alright, what is delta 1? Delta 1 is this little interval around C. Call this C plus delta 1 and call this C minus delta 1. And what is it? It's how close to C I have to get in order for the outputs of F to be within epsilon over 2 of L. What is the epsilon over 2? Maybe maybe it's better to sort of start the proof because it's not totally clear maybe what epsilon I'm talking about. So let me now be a little bit more careful and let's say begin the proof. So what do I mean by begin the proof? Well, I'm going to begin the proof, the actual proof that is the thing I'm trying to prove. How does it work? I receive an arbitrary epsilon, and then I do a bunch of stuff. Specifically, the first thing I do is I respond with a delta. I haven't figured out how to do that yet. So, but the very first thing I'm going to do is I'm going to take some kind of arbitrary epsilon greater than 0. And now I'm in the process of figuring out how to respond to that epsilon challenge. Well, now, here's what I do. I take that number epsilon, I divide it in half. I reach into my pocket for the thing I already know. And what I already know is that the values of f can be made arbitrarily close to L by taking x values sufficiently close to C. And so the epsilon over 2, the epsilon that I refer to here when I said epsilon over 2 is this epsilon. So I take my challenge, I divide that challenge in half, and then I go to my definition of what it means for the limit as x approaches C of f to be L, and I say, okay, how about epsilon over 2? Hey, limit, how close must I get to C in order for f to be within epsilon over 2 of L? And the answer is delta 1. So, what do I kind of know now? I'm gonna just squeeze this in right now. What I know is that if x is between C minus delta 1 and C plus delta 1, then f will be within L minus epsilon over 2 and L plus epsilon over 2. And now I do the same thing over again. Here I have some light switch in the way, so I'm just going to say challenge again with epsilon over 2. And there is a response. In other words, and that response is delta 2. What is delta 2? Delta 2 describes how far away from C, or how close to C, I should say, I must get in order that all these x values, when plugged into G, are off by epsilon over 2 at most from M. And okay, and so once again I got this challenge, and now it sort of took that number, this number epsilon, I divided it in half, and then first I threw that number at this limit, then I threw that number epsilon over 2 at this other limit. In both cases, since this limit really is M, it means that I can make the gap. I can force G to be arbitrarily close to M. In this case, I want to force G to be at most epsilon over 2 away from M. And there is always some interval of x values for which I can make G be differ from M by at most epsilon over 2. That's just what it means for this limit to be M. Okay, and so what is it that I know? Just like before, kind of repeating myself a lot, maybe that's good, is that C minus, if x is between C minus delta 2 and C plus delta 2, then the G function will be between M minus epsilon over 2 and M plus epsilon over 2. Okay, so here I have these kind of little sort of golden intervals, right? There's this little interval of x values that for any of those numbers, when I plug them into F, I'm off by at most epsilon over 2. For any of these numbers, if I plug them into G, I'm off by at most epsilon over 2. And now, if my error here is only half an epsilon, and my error here is only half an epsilon, then when I just add all these y values together to make the f plus g function, I'm going to be off by at most epsilon. So, okay, I think I'm ready. If you get this, then I'm ready to give an answer for what my delta should be. And the answer is, well, I just need both of these to be true. Okay? So if these are the magic numbers that make this true, and these are the magic numbers that make this true, I need both of those to be true. So I need x values that are within this interval and also within this interval. And so I just choose the smaller of delta 1 and delta 2. That is my actual answer. I receive this challenge, and I turn around and I say, okay, I'm going to set delta to be the minimum of delta 1 and delta 2. So just take the smaller of those two intervals. Okay, and now the whole thing just kind of happens, right? Because what is it that I'm trying to show again? I'm trying to show that within delta, blah, blah, blah. But if you give me now an x, okay, so maybe it's even best not to write anything else, but to just talk it out, right? If delta is the smaller of these two numbers, delta 1 and delta 2, then now, well, okay, I still need to prove the conditional, so I suppose I should do it. So now let's assume that that x is between c minus delta and c plus delta. Well, what is delta after all? Delta is whichever one of these two is smaller, right? Delta is the minimum of delta 1 and delta 2. So, if delta is the minimum of delta 1 and delta 2, then of course, delta is less than, okay, so if x is between c minus delta and c plus delta, then x is between c minus delta 1 and c plus delta 1. And also, x is between c minus delta 2 and c plus delta 2. Because because delta is the smaller of the two. So since delta is the smaller of the two, it's within both of these intervals. Okay, hopefully that's just clear. I can't go into any more detail on that. But that's just what it means to be the smaller of the to set delta to be the smaller of the two. So if I'm only delta away from C, then I'm less than delta 1 away from C, and I'm also less than delta 2 away from C. But now, reaching for the two statements in purple, what do I know? Well, by virtue of the fact that I'm within delta 1 of C, I know that F is in between L minus epsilon over 2 and L plus epsilon over 2. And if I'm within delta 2 of C, then M is between epsilon over 2 of G, and so I have both of these statements. What do? I just add these two inequalities. Okay, so it's property of inequalities. You can just do this, and what do I get? I get that L plus epsilon minus L plus M minus epsilon is less than F plus G, which is less than L plus M plus epsilon. And that is exactly what I wanted to prove. It feels kind of like magic, but what really happened here was I received a challenge in my F plus G function, and I asked myself, how do I respond? How close do I need to get to C in order to be off by at most epsilon? Answer, how close I need to get to C is just how close I need to get to C in G so that it's off by epsilon over 2, and how close I need to get to C such that F is off by at most epsilon over 2. And let's just, choose delta to be small enough that both of these hold, and then you just kind of add the two inequalities, and the whole thing is just kind of done. Okay, hopefully that made some sense. Goodbye!